Welcome. This video is going to take a closer look at aqueous solutions and how they can interact with each other in what we call double replacement reactions. And then another method of writing the reaction that's going on, which is referred to as a complete ionic and net ionic equation. So going back to aqueous solutions, an aqueous solution forms when water dissolves a solute. And that solute could be a solid, liquid, or gas, but it forms an aqueous solution or all liquid. And again, that solute could be an element or a compound. And if the solute is a compound, it could either be ionic or covalent. And most covalent solutes, like sugar or ethanol, exist as molecules when they're dissolved in water, meaning the molecule does not get pulled apart or changed in any way. It just spreads out in the water. But ionic solutes, which are referred to as salts, and this includes what we think of as salt, NaCl, as well as acids and bases, which are technically covalently bonded together, they undergo a change. They dissociate or get pulled apart by the water molecule because they have a positive and a negative end to them, a positive and negative ion. And so then these ions spread out in the water, and this is what we think of as electrolytes. So when you drink sport drinks and things with electrolytes in them, it's simply that the salt has fallen apart or dissociated in the water. It doesn't really change the salt, it just kind of keeps it in a suspended state until it either reacts with something else or it gets dried out and the solid reforms again. So double replacement reactions, remember, always start with two aqueous solutions as the reactants. And usually these aqueous solutions are ionic compounds dissolved in water or possibly an acid or base. And that means there will be ions floating free from each other since it's ionic and it's in water. After mixing, remember, one product will still be aqueous, but a double replacement reaction always produces either a precipitate, water, or a gas. And so the aqueous product that forms really hasn't undergone any change. Those ions were ions before, and they're still ions afterwards. So this is where we get this idea of simplifying the equation. So if you have the chemical equation, sodium hydroxide, NaOH, and copper chloride, CuCl2, can react to give you sodium chloride and CuOH2. And if you look at the products, the NaCl is still aqueous and the copper hydroxide is solid. So what I've tried to show in my picture here, and my picture didn't come through quite as clear as I'd like it to, the NaOH, because it's aqueous, the NaOH is really going to be Na positive ions and OH minus ions floating around in there. And the copper chloride, this chloride ion shouldn't be in there, that got misplaced. My formatting gets a little goofy when I poured it into this program. So this chlorine ion should actually be over here. So then you see my CuCl2, because it's aqueous, I've got copper atoms floating around. I guess that's just an extra one there. I got copper atoms floating around. I've got chlorine ions floating around. And then when I'm done, the sodium and the chlorine ions are still floating around, just like they were when we started. They're still floating around. But the CuOH2, and this should be up in the container, they have now formed a solid precipitate. So those ions are no longer free floating in the after picture. So here's the equation that I just showed you a visual for, so try and keep that visual in mind here. The complete ionic equation, what it does is for each aqueous substance you have, you write it as it really is existing. Instead of being two NaOH molecules or formula units in this case, it's really two Na ions, and I know Na has a +1 charge, and then also two OH ions. And I write them using a coefficient because they aren't connected to each other. These four ions are all free floating in that aqueous solution. The copper chloride is also free floating. There's just one copper, so I can deduce that it has a 2+ charge. The 2 chlorine, and again, even though it was Cl2, it's no longer together, so that 2 moves up here as a coefficient, and it's 2 Cl- ions floating around. And I don't use the AQ now because they're no longer expressing the compound I'm showing the individual ions. On the product side, the NaCl is still in the aqueous state, so I would write 2Na plus and 2Cl minus, and then the CuOH2 is a solid, so I show the entire formula unit because it's all together in the solution. It's probably sitting in the bottom if it's more dense than the liquid. So then the net ionic equation, the idea with the net ionic equation is that if you look, the 2Na was an ion before and it's still an ion afterwards. So it really hasn't participated or changed in this reaction. Same is true for the Cl minus. So these are called spectator ions, and just like in algebra, when you have like terms on opposite sides of the equation, they cancel each other out. So our net ionic equation is going to show the ions that actually participate or undergo a change, as well as the new product that is formed. And again, eventually the NaCl would be noticeable and would be a product if we dried this out. If we drove all the water off so it was no longer aqueous but became a solid, then we would have to write it as NaCl and show that that change was complete. But until the water is removed, the NaCl isn't technically going to form. So this is a complete ionic equation and a net ionic equation. So before I have you try a couple of them, just to kind of review here. Substances that are free ions in the equation are written as ions, not compounds. Spectator ions are the ions that don't participate in the reaction, so they show up on both sides. In other words, they're like terms and they cancel out just like you do in algebra. A complete ionic equation shows all the ions involved. And when you're writing your complete ionic equation, the phrase I like to remember is AQ is split in two. Your aqueous solution is going to split into a cation and an anion. And it's not unusual for your anion to be a polyatomic ion, and that's okay. And then the net ionic equation shows only the ions that participate, so this is where you cancel out your like terms. So here's one for you to try. Go ahead and pause and see if you can come up with first the balanced chemical equation, and then break that down into a complete ionic and a net ionic equation. So I'm going to go ahead and start working on my balanced equation. I have HNO3 and aqueous rubidium sulfide. I see that rubidium has a +1 charge. Sulfur has a -2 charge, so it's going to be Rb2s. And it's going to form aqueous rubidium nitrate. This is still a +1. And if I look nitrate up, it's NO3 with a -1. So this will just be RbNO3. And then dihydrogen sulfide, so that's telling me it's H2S. And this is the gas. And I'm not going to, well, I guess I'll go ahead and put the AQ in here so I know which ones to split apart. And so as far as balancing this, I need a 2 here if I could sneak it in. That 2 doesn't look so good, so let me try that again. 2 here, and then I'm going to need a 2 here. And that should balance the equation for me. And that you'll find that's quite often the case, that you just need 2 coefficients to balance a double replacement reaction. So then my complete ionic equation, both the reactants are always going to be aqueous, so you're going to split apart all your reactants. So I'd have 2H plus, 2NO3. The NO3 stays together because it's a polyatomic ion. 2Rb plus, and S2 minus. And then on the product side, I still have 2Rb plus, 2NO3 minus, and the H2S remains together. So as far as my net ionic, I'm looking for like terms that drop out here. So that would be my Rb and my NO3. So my net ionic is going to be 2H plus S2 minus forms H2S. So here's a second example for you to try. You've got aqueous solutions of sodium carbonate, manganese 5 chloride, forming the precipitate manganese carbonate. Now, it doesn't indicate what the second product is, but they tell you this is the precipitate, so this is going to be the solid. So we know that the other product has to be aqueous, and it's got to be made up of the other two ions. So since manganese is used and carbonate is used, my other product has to be sodium chloride. So sodium carbonate is going to be Na2CO3. Manganese chloride, since manganese is a +5, it's going to be MnCl5. These are both aqueous. And they're going to form Mn2CO3 That's my solid. And I said the other remaining two have to combine since it's a double replacement, and they need to be aqueous. And so now for balancing this, I've got 2 Na on this side. I've got 2 Mn on this side. So if I start with my metals, I'm going to go ahead and put a 2 here for the Mn. You maybe need a rap sheet for this, and that's fine. Go ahead and use it. And then if I put a 2 here for my Na, that helps my Na, but then when I get to my polyatomic ion, I've got some trouble because I have 5 carbonate on this side. So when I put a 5 here, my Na now has gone up to 10, so I'm going to have to come back and change that metal to a 10. And that works out just fine because now my Cl is 10. So if I just double check, I've got 10 Na, 5 carbonate, 2 Mn, and 10 chlorine, and that matches my product side. So then moving on to doing the complete ionic equation, my aqueous things have to split into two ions. So I've got 10 Na plus. I have just 5 CO3 because that polyatomic ion remains intact, minus 2. I've got 2 Mn. They have a +5 charge. And I have 10 Cl minus. On the product side, my precipitate is not going to break apart into electrolytes, so it's going to be Mn2CO3 and then my 10 Na plus and 10 Cl minus will remain electrolytes on the other side. So when I look for my spectator ions, my Nas and my Cls are spectators, so my final net ionic equation would be 5CO3 2 minus ions plus 2 Mn plus 5 ions yields Mn2 CO3 So that's an example of a precipitate, a solid precipitate, written out as a complete and a net ionic equation. For this last one, when we look through it, it says sulfuric acid, H2SO4, and aqueous potassium hydroxide combine to form water and another product. So this is the third possibility. You can have a gas, you can have a precipitate, you can have water. So if I go ahead and start with my chemical equation, I have H2SO4. Potassium hydroxide is just going to be KOH. This is known as a neutralization reaction because you have an acid and a base here, which always forms water and a salt. And remember, salt is an electrolyte. It's going to remain aqueous or dissolve easily in water. So water is H2O. And then again, this is a little bit tricky, but think of water as really being HOH. So this hydrogen and this hydroxide have gotten together. So that means my other product is going to be K2SO4. This is going to have to be aqueous since this is a liquid. And of course my two reactants have to be aqueous. I need to balance it. I have one SO4, one SO4. I have 3 hydrogen on the left side. I only have 2 hydrogen on this side, and I have 2 potassium. So balancing my metal first, that gives me 2 potassium. And then if I put a 2 here, that also balances the 2 oxygen and gives me a total of 4 hydrogen on each side. So that's my balanced equation. So then my complete ionic equation is going to be 2H plus SO4 2 minus plus 2K plus 2OH minus. The H2O remains together. 2K plus and SO4 2 minus or minus 2. So my net is going to be the H plus and OH minus, whereas the SO4s are going to cancel out and the K pluses are going to cancel out. So this is going to be 2H plus 2OH minus yields 2H2O. And if you wanted to simplify that to H plus OH minus yields H2O, you certainly can do that as well. And so this is, you'll see as we get to acids and bases that neutralization reactions always have this same net ionic equation. It's always H plus and OH minus getting together to form water.